Hello everyone, I welcome you to Engineering Thermodynamics lecture series. In last lecture we have studied what is system, surrounding and boundary. Now in this lecture let's see what is types of systems. Various type of systems that we are studying in this lecture. What are these types? We had listed out these system types in last lecture. The first type is open system. Okay, open system. So what is example of open system? Let's say we are having one container. In this container we are having water. If we heat this water with the help of burner, if we heat this water, then what happens? Heat is added to the water and this heat can transfer from this water to surrounding. From this flask it will transfer, from this walls it will transfer from here. Okay, this is what surrounding, and this water is nothing but our system. Okay, and this system is exposed to atmosphere. This system is open to atmosphere. So this type of system is nothing but open system. And if you see, not only heat but matter also can transfer from this type of system. This is open system, and when this water will get vaporized, okay, water vapors, these water vapors will transfer to surrounding. So matter as well as heat will transfer to surrounding. So Q and mass, okay, that water vapor has some mass, so Q will transfer and mass also will transfer. So that type of system is nothing but open system. The another type is closed system. So in closed system what happens? Suppose we are having one container and water is there. As we added heat to this water, what happened? Again heat will transfer, mass will transfer. Now what I am going to do? I am going to use one lid here and I will close this flask. Now it is perfectly closed. That mass cannot transfer from this system to surrounding. But yes, this is not adiabatic boundary. What is meant by adiabatic boundary? The Q will be 0. The heat transfer will be 0 in that case. Okay. So in case of adiabatic system, what happen? Q will not transfer. But here the boundary is not adiabatic. It is dithermic. So Q will transfer through this boundary. This is also part of boundary. This lead is now part of boundary. So from this lead the heat will transfer. Okay, the heat will transfer. But you can see the mass cannot transfer because there is one lead and that will restrict the flow of matter. That will restrict the flow of this water vapors. So mass will not transfer, but Q will transfer. Mass will not transfer. So this type of system is nothing but closed system. Now what is example or application of this closed system? If we say thermos flask, okay, we are having thermos flask. In that thermos flask what we do? We add or we kept water, we kept tea in that thermos flask, and after some time what happened? After 8 hours, after 12 hours, that heat in that tea will get transferred to surrounding and that tea temperature will lower down. Okay, so that type of system is closed system. But if you see tea quantity, that will remain constant in that flask. So that type of system is closed system. So what we can say? Q will transfer from system to surrounding. From surrounding to system is possible, but mass is not possible from system to surrounding and vice versa. Okay, in open system Q and mass will transfer from system to surrounding, and the vice versa is also possible. Okay, Q and M, heat and mass, will transfer from surrounding to system also. That is possible. The third type is isolated system. Isolated system. In thermodynamic application, the isolated system does not exist. The unique example of this isolated system is universe. Okay, so universe is the example of isolated system. So if we show this isolated system here, what is universe? So this is our universe. In universe there is system, and everything other than system is surrounding. So system will transfer heat to surrounding, or it will get heat from the surrounding. Mass can get transfer from the system to surrounding, or from surrounding to system, but we cannot transfer anything beyond this universe. Suppose this is universe. So what we learn, we cannot transfer anything from system to surrounding. Okay, that is impossible. Okay, this is impossible. We cannot transfer Q, we cannot transfer mass from mass outside the universe. So we can say the universe is nothing but isolated system. So what is our definition? We cannot transfer Q, that is heat. We cannot transfer matter or mass from system, from universe, okay, or from isolated system. So that is what the universe is, what isolated system. In exam, if they ask what is example of isolated system, there is unique example of isolated system, that is nothing but universe. Don't say thermos flask is a isolated system. In some books thermos flask given as an isolated system, that is wrong. It is closed system example, because we know in isolated flask, if we kept tea or water, hot water, its temperature will lower down after some time. Why it will lower down? Because there is transfer of heat from system to surrounding. Okay, so it is example of closed system. There is another example of closed system. We can say when we study this typical cylinder piston in thermodynamic study, always in each lecture you have to study this typical system cylinder piston. See, when there will be combustion, what happen? We know 4-stroke in IC engine, that is suction, then compression, then expansion, that is power stroke, and exhaust stroke. During suction, what happen? Inlet wall is open. During exhaust stroke, exhaust wall is open. So during suction stroke and exhaust stroke, that particular mechanism is open system. It will act as an open system. Why? Because airflow mixture will come inside. This airflow mixture will get burned and combustible gases will escape out in exhaust gases. So during suction stroke and during exhaust stroke, this mechanism will act as an open system. But we know during compression and during expansion, this inlet wall and exhaust wall are closed, right? So mass will not transfer from this system to surrounding, but yes, heat will transfer. Okay, there are fins given, right? If you see your two-wheeler engine, outside your engine you can see fins. Through these fins heat will transfer, right? For optimum cooling only that fins are given. Okay, so there is always heat transfer. Just touch that engine, you will feel some heat. So heat will transfer from this system to surrounding, but mass will not transfer during compression and an expansion stroke. And so during compression and expansion stroke, this mechanism, cylinder piston mechanism, will act as a closed system. So do remember this example. At the time of oral you can explain this, you can tell this to external examiner. So this is about open system, closed system and isolated system. Also there is one concept, that is control volume. This is also interesting. For online exam they ask what is control volume. Now see, what is control volume? We have studied this application in last lecture. There is one impeller here. What this application is? It is centrifugal pump. Okay, this impeller is rotated by using one motor. So when it will rotate, what happen? There will be negative pressure here. There will be positive pressure at suction side. Okay, so water will get pulled, and there is delivery side here. Okay, so when we say control volume, the volume is fixed, but mass is moving, and the discharge rate is same. Suppose this is our boundary, section 1 section 2 this is our boundary, and inside this boundary the volume is always fixed. But you will say, so water is coming inside, so how the volume is fixed? Suppose the water coming inside is 15 liter, the same water will get displaced, or same water will get transferred or delivered through this section 2. So here water inside is 20 liter. Okay, 15 liter is added, 15 liter is leaving, so always the volume inside is 20 liter. So this volume is control volume. This way we say the volume is control volume. And which type of system it is? It is open system. So when we say control volume, we use this concept in open system always. Okay, so that you have to remember, because water is coming inside from outside the system and it is leaving the system. Okay, so mass will transfer from open system. With that mass, heat also will get transfer, some internal energy also will get transfer. So that's why this type of system, the control systems, are always open system. So do remember this. This is important point for online examination. Now after this, let's study some basic concepts that we are using again and again in the analysis of thermodynamics, that is state. So when we say state, that is thermodynamic state, then path, process, cycle. Of course, a thermodynamic cycle we are talking about here, thermodynamic processes, thermodynamic state. So all these concepts we have to learn. Let's see this one by one. When we say state, we say state of system always, state of system. So when we say state of system, then that is nothing but a condition of a system at an instant. So let's learn this state concept with the help of cylinder, piston again. Here the piston is at TDC. Suppose this is TDC position, this is BDC position. So if combustion happens, suppose there is air-fuel mixture we are using as a system. Suppose the combustion happen, then this combustible gases will push piston down. So this piston will move from TDC to BDC. So what happened? There will be displacement, right? There will be volume displacement. This piston has circular cross section, so distance L it will travel. That L into cross section area, that is nothing but delta V. Okay, so how much volume it will cover? It will cover delta V into L. That much volume, the cross section area into L, that much volume it will cover. So that is nothing but displacement volume. And to do so, what we have done, these combustible gases will push this piston down with pressure P. So this P into delta V is equal to work done. Now why I have written this 1-2, okay, for work done. So I have written this 1-2 because I have got this work done during process 1-2. Okay, during process 1-2, the piston was at the position 1 and now it is at the position 2. So during this process 1-2, what happened? This piston has moved and the properties of this system had changed. Okay, so that properties we have to analyze here. That's why I have written 1-2. Now this position 1, when piston is at TDC, the position was 1. Now piston is at BDC. After moving this piston will come to this BDC, and that will be position 2. So when I will say state, that is nothing but position of a piston, that is position 1 or position 2 or condition 1 and condition 2. So when we say state of a system is 1, then we analyze various properties of the system at state 1. For example, suppose we have to analyze condition of a system at state 1, and means we have to read various properties of this system at state 1. So what I will say, at state 1 the pressure is P1, that is one of the property, temperature is T1, volume is V1, is enthalpy here is H1, specific enthalpy, then internal energy at this position is U1, okay, entropy is S1. So this way we read various properties of the system, okay. So and we call it as state 1, okay. The position of the system is nothing but state 1. Then state 2, piston will move from TDC to PDC. Why it will move? Because this combustible gases will push this piston down. Now you tell me, the pressure was P1, okay, and when piston will move to TDC, his pressure will change to P2, right? Pressure will change to P2, the temperature is changed to T2, volume is changed to V2, here enthalpy will change to S2, internal energy will change to U2, entropy will change to S2. You may don't know this entropy concept yet. We will study this entropy concept in second unit. So this way properties will change, okay. So at state 1 these are the properties, at state 2 these are the properties. Now see, this property we read at particular position or at any instant we can read these properties. Suppose the piston is here and we stop the phenomena, or we stop we stop this moving piston at this position. Suppose this position is A, any position, mid position A. So what are the properties at this point? At this point the properties are PA, TA, VA, okay, all these properties we can write like that, okay, at this instant. So when we measure properties at any instant, that is nothing but state. How can we show this graphically? We have to draw indicator diagram. For that also I will tell you what is point function here. Suppose I have drawn one characteristic, that is PV curve. We also called it as indicator diagram. So here you can see I am going to plot pressure versus volume, P on y-axis, V on x-axis. Now see, the position 1 I am going to mark. At position 1, how much is the pressure of the system? We are using here any gas. Suppose we are using methane gas. At position 1, how much is the pressure of the system? P1. That I am going to mark. Suppose this P1 is here, okay, here I have marked. And how much is the volume? Volume is V1, that I have marked. So I am getting 1 point. I can mark T1 also. To mark this T1 I have to use another axis, that is Z axis, okay, or T1 axis. Here I am using only pressure and volume, 2 axis. So I am going to mark this point in space with the help of these 2 values. So P1 I have marked, V1 I have marked. So here I have got the point. Now see what is point function. By using these properties I can define the condition of a system. So what is condition of a system here? The condition of a system is 1, and I am using this 2 properties, pressure and volume. I am going to define that condition. That's why this pressure and volume are the point function. Okay, so do you got what is point function? By using a single point I can define the system condition. Okay, so here I will say at this condition or at this position 1 the pressure is P1, volume is V1. So that's how I have defined the system condition. Now what is condition 2? In condition 2 the pressure has increased up to P2, see, and volume has increased up to V2. So here this way parabolically it had changed from 1 to 2, it had changed. So system had changed its position from 1 to 2, TDC to BDC, and I have to read now the condition of a system at state 2. Was the condition? The pressure is P2 and the volume is V2. So this way we can define the system by using a single point. That's why pressure and volume is a point function. Now see, to do so what we have done? Process 1 to 2, right? The process 1 to 2 happened. That's why the condition has changed from 1 to 2, right? Now see what is path. Here you can see we can define system by state 1. We can define system by state 2. Okay, and we have reached to state 2 from state 1 by this path. So this is nothing but path. Okay, so this is thermodynamic path. Here when we say path, we have not defined its nature, means it is parabolic or it is hyperbolic or it is parallel to v axis or it is vertical to p axis. Of course here we can see it is not parallel, it is not vertical, it is nearly parabolic, but that is my judgment. Actually I don't know its exact nature, so that I have to analyze. If I know its nature, that will be the process 1 2. It is, let's say it is adiabatic process, let's say it is constant volume process, we can say it is constant pressure process. Suppose it is parallel to V, means it is constant pressure process. Here process 1 2, here I will show you. See, this is what path. I have defined state 1, I have defined system by state 1, I define system by state 2. Now I don't know its nature, then we can say path 1 2 simply. Okay, but if I know its nature, here you can see it is parallel to v axis, means P1 is equal to P2 we can say. So P is equal to C. So we say it is isobaric process. We call it as isobaric process. I will tell you these processes one by one that we have to learn in detail in next lecture. Here just I will show you what are the various process and why we call it is process. Okay, when we don't know its nature, it is path 1 2. If we know its nature, means it is parallel to v axis, or here during this process pressure is constant. During this process here you can see the volume is constant. Okay, it is vertical perpendicular to this v axis or parallel to p axis. The nature is known, it is constant volume process, or suppose temperature is constant, it means isothermal process. The temperature is constant during change in position or change in state. This point 1 is called state, point 2 is state. So state will change from 1 to 2. So path 1 to 2 it will follow. And what is its nature? T is equal to C, that is isothermal process. Okay, so the process is isothermal. Okay, so we know what is state, now we know path, and we know what is process. We will see what are the various process in detail in next lecture. Now see what is cycle. Suppose we are going to draw various processes here. This is process 1 2, which is, let's say T is equal to C. Then we draw one another process which is adiabatic process. In adiabatic process S is equal to C or Q is equal to 0, the heat transfer will be 0. Then another process, that is 3-1, which is constant volume process. Now if you see, the cycle has started from 1 and it ends at 2. This process has started from 2, the next process has started from 2, it ends at 3, and where this third process has ended, it get end at point 1, which was the initial point. So when the end process will get end at the initial point, that is nothing but a cycle. Okay, it will execute one cycle. So this is nothing but thermodynamic cycle. This area is nothing but work done. On PV diagram, what area we are getting, closed area, that is nothing but work done. So that is about state, path, process and cycle.